If you are a fan of comic books and related cartoons, television shows, and movies, you are aware of a man that was accidentally exposed to gamma rays. Because of this exposure, he turns into a green monster when angered, which is a marvel. This may be a great storyline, but gamma ray exposure leads to serious bodily damage, not superhuman powers. Gamma rays have the most energy of all of the electromagnetic waves. Before we practice calculating how much energy gamma rays and other various electromagnetic waves possess, let's review the basics regarding electromagnetic radiation. A vibrating electron generates an electromagnetic wave, which is two waves perpendicular to each other. One of the waves is an oscillating electric field, and the other is an oscillating magnetic field. The faster the electron vibrates, the smaller the wavelength, lambda, but the velocity is always constant, the speed of light, 3.0 times 10 to the 8 meters per second. B is the oscillating magnetic field. E is the oscillating electric field. C is the speed of light. Lambda is the wavelength. Wavelength is the distance between successive peaks of the wave, crests, or between successive low points of the wave, troughs. Frequency is how many wavelengths pass a certain point per second. Wavelength and frequency have an inverse relationship. As one goes up, the other goes down. C equals lambda F. Let's talk about the different types of electromagnetic waves. The electromagnetic spectrum is the range of electromagnetic waves ranging from the shortest wavelengths, gamma rays, to the longest wavelength, radio wave. A general rule to follow when determining the energy of electromagnetic waves is the shorter the wavelength, the higher the energy it possesses. E equals HF. E is energy in joules, J. H is Planck's constant, 6.26 times 10 to the negative 34 joules per second, Js. F is frequency in hertz, Hz, which is 1 per second. Let's practice using the energy equation to determine the energies of different electromagnetic radiations. Determine the energy associated with an X-ray whose frequency is 3 times 10 to the 17 hertz. The frequency is given, so all we have to do is plug it in along with Planck's constant into energy equation. E equals HF. E equals 6.626 times 10 to the negative 34 Js times 3 times 10 to the 17th times 1 over S. E approximately equals 1.99 times 10 to the negative 16 J. Let's do another one. How much energy is associated with a microwave whose frequency is 1.7 gigahertz? To solve this, we use the same equation as before, but we need to convert gigahertz to hertz. The G represents the prefix giga, which is 10 to the 9. E equals HF. E equals 6.626 times 10 to the negative 34 Js times 1.7 times 10 to the 9 times 1 over S. E approximately equals 1.13 times 10 to the negative 24 J. One more. How much energy was associated with the gamma ray that struck our superhero character if the frequency was 1 times 10 to the 20 hertz? Energy equation to the rescue. E equals HF. E equals 6.626 times 10 to the negative 34 Js times 1 times 10 to the 20th times 1 over S. E approximately equals 6.63 times 10 to the negative 14 J. The photoelectric effect is the phenomenon whereby electrons are ejected from the surface of a metal when electromagnetic radiation is shown upon it. Albert Einstein won the Nobel Prize for this in 1921. What he discovered is that the frequency of electromagnetic radiation shown on the metal determines whether electrons are emitted from the metal. The intensity of the light only had the effect of more electrons leaving the surface, not whether they leave the surface. We have just learned that frequency is the factor that is used to calculate the energy of electromagnetic radiation. Therefore, the energy of electromagnetic radiation is a common factor in determining whether electrons are emitted or not. The minimum frequency that will cause an electron to be ejected from a metal if light is shown on it is called the work function, W. Each metal has its own work function value. Any frequency greater than the work function frequency will cause the same number of electrons to be emitted, but with higher kinetic energy, which is the energy of motion. Gold is a popular metal. Let's see what minimum energy and frequency of electromagnetic radiation is required to eject electrons from gold. Gold's work function is 8.17 times 10 to the negative 19 joules. We now apply the energy equation. F equals E over H. F equals 8.17 times 10 to the negative 19 J over 6.626 times 10 to the negative 34 JS. F approximately equals 1.23 times 10 to the 15 Hertz. This frequency of electromagnetic radiation is in the range of ultraviolet light. What this means is if you have any gold jewelry on and you go outside into the sunlight, electrons are flying off of your gold. Electromagnetic waves are generated by vibrating electrons. They have two wave fronts that are perpendicular to each other. One is an oscillating electric field, and the other is an oscillating magnetic field. The wavelength of an electromagnetic wave is the distance from crest to crest, or trough to trough, measured in meters. Its frequency is inversely related to its wavelength, and is the number of wavelengths that pass a point per second measured in Hertz, Hz. The electromagnetic spectrum is the range of electromagnetic waves from the smallest wavelengths, gamma rays, to the longest wavelengths, radio waves. The energy associated with an electromagnetic wave is given by Planck's constant, 6.626 times 10 to the negative 34 Js, times its frequency. E equals Hf. The photoelectric effect is the phenomenon whereby certain frequencies of light shined on metals can cause electrons to be ejected from the metal surface. Each metal has a minimum energy required for electrons to be ejected, which is the work function. Increasing the intensity of the electromagnetic radiation beyond the work function of a metal will cause the same number of electrons to be ejected, but at higher kinetic energies, which is the energy of motion. The intensity of light only causes more electrons to be ejected, but only if they are ejected in the first place.